question 1 is about y equals mx plus c, and the idea of lines being at right angles to each other. And it's not a bad idea just to have a picture in your mind that if the gradient of this line, for instance, is b over a, the gradient of a line which is effectively being rotated 90 degrees will have this here would be, gradient of this line would be a over b, but also there's a negative sign in front of it. So it's just the negative reciprocal. Try to get to grips with that if you can, because it's the idea of being at right angles or being orthogonal is important later on. Now then, most of us were okay with this. There is a bit of a theme here in your maths, and that is that sometimes we need to rewrite something to get it into a form which is more useful, and we're sort of preparing our functions, etc. So this kind of preparation is very important to us because it's in gradient intercept form. Often talk about standard forms of quadratics or functions, etc. And then we've got our gradient. The gradient of the other line that we've got clearly is equal to 2. Just watch out that it's the negative reciprocal, not just the reciprocal. Watch out for little bits like this with simple questions. Make sure that you take your time over it. Some of us may be forgetting to divide the 3 by the 4 at that stage. Anyway, you should have, of course, that y is equal to 2x plus 7. The second part of this was finding a point of intersection, and that's really a headline for us in our maths, is being able to calculate points of intersection. So if that's something you're not happy with, make sure you go over that. Here we are simply going to use simultaneous equations, and we use simultaneous equations each time we want to find points of intersection between lines. I'm not going to go through this one. This is a simple one. This is a linear simultaneous equation, and you just work through it. So that's enough said about question 1. Question 2 was about indices. So let's have a look at that, and that is worth a quick mention. So we'll see what you had to do there. The question said solve 16a squared equals 2 root a. And the idea with this is that you could just get a on its own, and there's 1 or 2 bits and pieces that you could do. Just to help you with your maths further down the line, I'd like to go through an approach which is sort of inappropriate here really. It's overkill. However, it is going to be useful later on down the line to sort of look at some factorising. So it's not necessarily the way we would do it at AS, but it's worth a look because it is quite interesting really. Getting 0 on the right hand side is useful, and just writing it in index form is useful. Writing things in index form is often a good thing to do, whatever you're doing, whether it's some integration, differentiation, etc. And then at this point, it just wanted to sort of have a look at a way of factorising, and you have to say, well, A is in both, but which index are you going to use? Is it 2 or is it half? Well, you make the same choice as you would do with simpler questions. You look for the least. So which is the least? Half. So you can just say 2a to the half is what you're going to do. And then you've got 2 times what is 16. And then this bit is the nice bit. It's actually very, very simple. So just slow down and make sure you're okay. When you're multiplying, you have to add the indices, and we've got a half plus what is 2, 1.5, and obviously the 1. That's quite nice because you get straight away that a equals 0 is part of the solution, which was missed in some cases, and also that 8, a to the 3 over 2 is equal to 1. And just to be a little bit different, to get a on its own, we're going to multiply both sides by 8 to the minus 1. That's a over the top way of saying divide by 8. And the other thing that we're going to do, which is maybe a little bit over the top approach, is just to raise them to the power 2 over 3. The reason for that is that we know that if we have a power and we raise it to this exponent here, that the rule is you multiply the two exponents and that will give you a to the 1. So you have to have a to the 1 in this question, and that's of course equal to just 8 to the minus 2/3. That last little bit, just tidying that up, is just GCSE. That's 1 over 8, and remember the bottom fraction is the root part of it, and the top part of the fraction is the index part of it, which equals 1/4. A little bit over the top, but worth seeing. The second part was done well, and we're just going to mention a couple of things with solving quadratics. The question said b squared, sorry, it didn't say b squared, it said b to the 4 plus 7b squared minus 18 is equal to 0, and you had to solve it. Some people went down the route of saying big B is equal to b squared, that's fine. Others were able to factorise it straight away just in terms of b squared. And do that, and a little bit of factorising should give you a +9 and a -2. What was nice is that people were saying b squared equals -9. In other words, they were continuing with it, and then in this question we wanted all the real solutions, so we continue with it anyway, and at this point we then say ignore. In other words, it doesn't fit what we're looking for. So that's always a nice thing, to just write down everything and then say which bits you're ignoring. You're giving a really full answer there, which is very nice to see, I think. B squared is equal to the square root of 2. Some of us, sorry, b squared is equal to, I'm losing my marbles, sorry. B squared is equal to 2, therefore b is equal to, some of us just putting root 2, but of course there are two numbers that when you square it give you 2. There's the plus version and the minus, plus root 2 and minus root 2. Just a little point, be really confident about these square root symbols. If you're asked to evaluate the square root of 25, it's just one number, 5. It isn't +5 and -5. So this symbol represents the positive square root. It's not the same as asking to solve x squared equals 25. Then x really is equal to +or -5, if that makes sense. So just watch out for that. The square root symbol is just one number. It's the positive number. It's not the same thing as saying solve x squared equals 25. Maybe I'm going a little bit over the top with that. Right, question 3 was your integration question. So we shall have a look at that. And you've got to do both indefinite and definite integration. It's worth, when you look at some bit of maths, to say to yourself, what kind of thing have you got? What kind of mathematical object is this? Is it a number? Is it a function? Is it a vector? Etc. And that will simplify things in your own mind, that you can just think of that entire thing here as a function. This one, because it has these numbers in, this definite integration, this entire thing can be thought of as a number, and as such you can do things with that entire expression that you can do with numbers, like for instance put an absolute value on it if you want to, the absolute operator on it. Anywho, let's have a look at the first bit. So we've got the integral of 4 over x cubed plus kx dx. Just a note about notation. Tidy it up, that was a theme, preparing functions, etc., so it's easier to use, and in this case I think we did well with it. I am seeing this kind of thing where people miss out two important aspects of their communication. There must be brackets, please, and there must be a dx. The dx is important because look, there's two letters here actually, and you want to just be clear that you're integrating with respect to x, and that here you've just got this k, in this case it's just a constant. The other thing is that you are applying this to the entire function, so we have those brackets. And so just remember, keep your brackets. You had them in the question, just keep them within your working. The students, I think, who are doing well on this were quite systematic. They had got certain things in place which were automated, and that means that you're not having to think too much about it. So you've got x, add 1 to the power, divide by the new power. Careful, there's a temptation to maybe miss the minus sign there. Just watch out for that. There isn't a power, they just put 1 in, add 1 to the power, and divide by the new power. All right. What this function represents, this entire thing represents a function. It's the function that when you differentiate it, you get this. And it's a good idea just to differentiate your answer to check that you are getting the thing up here, and you are. The only thing is that you could have a number here, let's say plus 2 or 3, and when that term gets differentiated, it just disappears. In other words, there's lots of functions that when you differentiate give you this. So you must put in that c, which just represents any constant term. That was missed by a few people, and if possible, just tidy up so our final result should look something like this. It doesn't matter whether you put k over 2 or half k. I don't know, it's just me, I like having these kind of things separated. I like to see that number, but it really doesn't matter too much. Anyway, that's your final result. So a few people for getting the C's. Let's have a look at the second part of this. I think actually I'm just going to have a new sheet of paper for it. I want to write down the question, the 0.2 and the 0.5, and then 4 over x cubed plus kx dx was equaling 8. So this of course represents a number. In fact, the number is the number 8, and they're being quite clever here. They're forcing you into not using your calculator for it. Try when you're communicating, lots of people are doing this, which is really nice, just have line after line and you kind of just chipping away at things and rewriting them. Careful with your notation. I kind of realised that this is my fault because a lot of us missed out the square brackets, and that's an indication to me that I haven't pushed that enough. So that's the notation we want to see at this stage, not the elongated s, but the square brackets when we've actually integrated that function. The other thing is don't leave it like that. Not that you'll lose marks for it, but it's just really nice just to have these sentences making sense and following on from each other. You were forced into doing the full substitution. We often talk about full substitution as a bit of a headline, so we will put that in. And it's just take your time over it. Please don't rush these things, and certainly under exam conditions don't try to show off too much and sort of say, oh look, I can skip a couple of stages because I'm mentally athletic. Don't do that. You're communicating, so you have to put in all these bits. And I know it's not a problem for me because I'm not mentally athletic, but I know for some of you are. Just remember you're going to get marks for your working. Again, I want this sentence to be repeated underneath, and so I'm going to finish off this line with the equals 8. So each line is saying the same thing each time. We've got that and that. They follow on from each other. So this is good communication. Just watch out for a few things. These negative signs, we know they're going to cause problems for people. I would do this bit in the calculator first and then that bit and start to chip away at things. So all of this bit we can certainly do in the calculator. So we've got minus a half plus 2k, and then here we've got minus 8 plus an 8th k is what we've got. Again, just watch out for your setting out. It's very nice if we have that complete sentence and put equals 8. And just keep working with it. We've got to see evidence that you have worked through this, so just put each stage in. You've got time to do it, remember. So anyway, that eventually gives us 6d plus 15k equals 64. Just multiplying through by 8 to help things out a little bit. We don't like fractions, just multiply everything by 8. Make life easy for yourself. Just as a general rule, if you've got things on the bottom like this 8 here, just multiply everything through by 8. Anyway, you've got k is equal to 4 over 15. So I think that's enough on question 3. Okay, question 4 was a linear model question, and there is we talk about headlines in mathematics. The headline for one of the headlines in AS Maths is modelling and having graphs that represent something in real life. Way back in year 7 in your science, you did some very, very good work on something that they call line graphs, which are just graphs that could be curved or straight lines, and you had some points and they represent something in real life. It's very, very good stuff actually. Let's just draw a graph to help us. It's always a good idea. So this is the height of a tree, so 3 and 2.35 was one of the points, and the other point was 6 and 3.28. So that could be really useful for you to kind of just have a bit of a sketch of it. In actual fact, this whole question reduces to, can you work out the equation of this line? Certainly not going to go through how you calculate that here, other than tell you what it should be. We can interpret this thing as well. When t is equal to 0, of course you get this part, the intercept on the y-axis. In other words, when t is equal to 0, 1.42. So that's your picture, that's your model. And again, link it back to the work you did in Key Stage 3 in actual fact in science. The whole purpose of having a line like this, a graph, was that you can then use it to make predictions. And just moving on from that and developing it, our model then gets a little bit more sophisticated. Rather than using a graph to represent reality and make predictions, we've got a formula. So that's the next stage of it really, is creating a formula to represent reality in some way. So that was a really nice question. And the last bit was, here's a point. You had to say the height of the tree was approximately 140 and it's planted. Explain. You know, when you have a wordy question, think about the idea of, ask yourself the question rather, is there an opportunity to calculate a number? If there is that opportunity to calculate a number, then do so. And in this case, it says initially the actual height of the tree was 140, and we can say from the model, something like that, from the model, the initial height is 142 centimeters. Straight from there, and put this is close to 140 centimeters, so supports the model. Look, with these models, it's really close to it. So don't sort of say, it's not right. It's not going to be exact. It's just sort of trying to model reality, and so that's really nice. So with explain type questions, or questions where there's maybe a sentence as an answer, always think, is there an opportunity to calculate something, and give some numbers in there as well. So it seems like you have to do a fair bit of work in there, but anyway, that's enough of that. Question 5 was your first differentiation question, and you were introduced to the idea of a gradient function. So just watch out for this when you're asked to differentiate. Do put the notation in. Please don't be sloppy with your work. Put in these little bits, dy by dx. You must include that. You're telling the examiner what it is that you're doing. Don't just differentiate the thing. I'm not even differentiating the thing. Sorry. So you've got, let's differentiate it, 6x minus 24x to the minus 2 is what you've got. most people are absolutely fine with the differentiation. 3 marks for that. It's very nice. And what we've got here with this, in particular with this specification, they're trying to get you to apply your skills straight away. And here we've got hence find the exact range of values for which the curve is increasing. So it's a very nice idea. In other words, we've just got to solve if the curve is increasing, it means the gradient function is always positive. So that's what you're trying to solve. Let's have, your communication is saying, can you have a sentence underneath? Which is, just sort of rewriting things. Yeah, we can. And then we continue to solve. I'm not going to finish that off, but you can do that a little bit. Question 6 is a GCSE question, which we get at A level. What's interesting is a lot of us got very good results at GCSE, but this would be a question where it's possible to get a grade A at the end of GCSE and not get this one right. So it is a difficult question. You've got to know the area of a non-right angled triangle. You've got to know the formula for that, and you've also got to know the two formula that we use for working out unknown lengths and angles in non-right angled triangles, namely the sine rule and the cosine rule. What some of us are doing is launching into the sine rule, which is not a bad idea if you can't spot which one to use because it's the quickest one. If it's not working for you, then obviously go into the cosine rule, which was the thing that you were supposed to be using here. Was the cosine rule. All right. Let's not do that one if that's okay, because it was a GCSE question, and rather have a look at question 7. So this was very nice. This is a question about points of intersection, which of course is one of those big things in AS Pure, finding out where lines cross. Just before we launch into this, there's a couple of things that you might be familiar with, and that was the use of simultaneous equations to find where a quadratic and a straight line cross. So you might have those two equations, one was quadratic, one is linear. Solve them, in other words, find the points of intersection of a quadratic and a linear. And also it may be the case that we just have one point of intersection, in other words a tangent, and it also may be the case that there are no points of intersection. So the whole key to this was the discriminant, because the discriminant is used to tell us how many roots there are to a quadratic. We can do the same thing actually with circles. They also, when you're trying to find out points of intersection, etc., will lead to a quadratic. Okay, so let's have a little look at that. What was brilliant about this, I really like this question, because what was brilliant about it was neither a quadratic nor a circle, and yet reciprocal graphs, an intersection of a line and a reciprocal graph is also going to lead to a quadratic. So very nicely conceived question from the exam board here. You are supposed to know and be able to sketch a reciprocal graph from memory. And you're also supposed to appreciate that if you multiply this by a number, let's just call it k, that you get a stretch in the y-axis, and that has the same shape. I say k, it could be k squared, it's still just a number, so it's still just a stretch in the y-axis by scale factor k squared, so that's the shape remains the same. We can go a little bit further and say what happens if you add 1 to it, then the whole thing gets shifted up by 1. So we have a graph that looks like that. I am going to put the x and the y in there, not that you've got marks in this case for it, but this is a 3-mark question for sketching y equals k squared over x plus 1. How good is that? 1 mark for this quadrant, 2 marks for getting both of them, another mark for getting the asymptote labelled up. So really good. Sketches, put the labels, your axes, and label any salient points, whether it's asymptotes or in some cases, if it's clear that it is needed, maybe some points of intersection, etc. But that's absolutely fine. That's all we need for this one. Now, just like these kind of questions, you had to show that if you're solving a simultaneous equation with this and the line y equals minus 2x plus 5, that it leads to that. I'm not going to talk about that. That is up to you to sort out. However, it is just worth making a few points about this equation, because one thing that you must be very, very comfortable with at this stage is the idea of the discriminant. And of course it's that part of the quadratic equation which is in the square root, and if you've just got one root, in other words it's just touching, then you're going to have this result here, that the discriminant is equal to 0. What I think we should be aware of is, first of all, look how you've got your quadratic in standard, I've written squared there, sorry. Look how you've got your quadratic written in standard form, and that this is the A part, that is the B part, and that is the C part. So that's, you know, there's a few ideas here. First off, the idea of writing things in a particular way, a standard form of writing quadratics, and that makes it so much easier to do the full substitution in that particular case. I'm not going to carry on with that. If you're not happy with discriminants, please read up on them. Question 8 was our binomial question by two numbers, and the two numbers are 2 and 3x over 4. If you can, try to make routine things really automated. So practice, 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 just this sort of stuff, so that when you're doing your questions, you don't have to think about it at all. It's not taking up any effort, it just becomes sort of automated. So there are a few things like this that you can do where you don't have to worry, and it doesn't matter if it's a bit long-winded. So I would just want to, as a bit of a demonstration, show you, for example, that binomial expansions can be like that. And this is in ascending powers of x. No x is 1x, 2x. You know, I can program a computer to do this. It's also got to add up to 6. 6, 5, 4. I then got to put my coefficients in. I put those in, and they all start with 6. And then there's a choice of the numbers on the bottom. Oh, which one do I put, 6 or 0? Here's the good news, it doesn't matter. I'm just going to put the smaller of the two. Is it 5 or 1? It doesn't matter, because it gets the same result. 4 or 2, doesn't matter, just put those in. So I'm not going to go any further than that, because you can work that out. So the advice here with binomial is make sure that you've got a really sort of easy way to do it. It's not necessarily about doing it really quickly. It's about knowing that you've got a way that you don't have to revise for, that you feel is going to be very sort of robust under exam conditions. So that's what I would go for. I wouldn't necessarily go for doing things quickly, but doing them in such a way that you know is going to be robust. It then says something where you've got 1.925 to the 6 you've got to use your part of your expansion to say what this would be. You've got to explain what you have to do. Let's just put this here and say, oh, you know, if it was equal to that, then what I could do is, if I can find an x here where this entire, in other words, if I can make 1.925 equal to 2 plus 3x over 4, then I could substitute it into the entire expansion. Let's just carry on with this. X equals minus 0.1 is what you've got. So all we're doing is setting these two things equal. And here's the thing. If x is equal to minus 0.1, then in this expression here, the entire thing becomes 1.925. So, like we've had before with, you know, explain type questions, it may be an opportunity to, you know, get a number out, and we do want a number there as well as some words as well. So you substitute x equals minus 0.1 into the 3 terms of your expansion. There is something that's worth mentioning here. I've never actually seen a question like this done on this kind of expansion. You see this again in year 13, something called general binomial expansion. But what they're saying is, in this case, to get the real proper answer, we'd have to do the full expansion. However, of course, what is happening, because this is really small and it's less than 1, when we've got these terms like x squared and we'd have x cubed, etc., the following terms become very, very small. So much so, in fact, that we have got a way of finding an approximation to 1.925 to the 6. So a surprisingly large amount of work to do in this one, just for the 1 mark. But nice to see, because that will help you in year 13 when we do general expansions, whatever they are. Question 9. So one of the things that we had before, we've had a model. It was the tree question. I think it was question 4, I can't quite remember. A linear model to represent something in real life. And we said that brilliant stuff you did in science way back in Key Stage 3. And now you've got something similar. Again, you would have maybe seen something like this in science really early on, where you've got something in real life and you can draw a line for it. The thing I would do here is I would sketch the graph, put in some values, n equals 0, t equals 0. The other thing is, can you see this? Sorry, can you see this term here? N minus 2 all squared times by 3. That's always positive. So if you're taking away something, this is starting to reduce. You know, give me an n. As n increases, this thing is starting to sort of, what is happening to it? It gets big to a point and it reaches a maximum point. Now then, this is a bit like completed square form, isn't it? Can you notice here, when n is equal to 20, this would be at its smallest. So in other words, t would be at its biggest. Gosh, that was laboured. I'm sorry. Anyway, your quadratic, you know it's minus n squared. You know it's going to be one of these sorts of things. And it reaches a maximum at 1200. If you're not happy with that stuff, just go over the stuff on completing the square, and interpreting a quadratic in completed square form is really useful. So we've got this sort of thing. I want to just jump ahead a little bit to part D. It says state giving reasons the limitation of the values of n. Now then, a bit like those explain questions, is there an opportunity to get a number out? Yeah, there is. It's the 20 actually. Now look, what happens, I think for some of us we knew that when n exceeds 20, t would be negative, and that would be no good. But also, if you read this carefully, it says a company started mining tin in Riverdale, and then it says a model to find the total mass of tin. In other words, t should always be increasing, because it's sort of, you know, how the total mass since the beginning that the company's mined. So we get a maximum here at this point. So we know that n has got to be less than 20. And the reason for that is since t must be, or must be increasing is okay to say, must be increasing. I kind of, part of me wants to just change that a little bit and say n must be less than or equal to 20 since t cannot decrease. However, it doesn't matter whether you've got a soft or a hard inequality at this point. They're not going to worry too much about it. But the idea is that we've got to say the limitation is n is equal to, n can't be any more than 20, since t must be increasing. Maybe a bit better to say t must not decrease. That's fairly straightforward. Calculate the mass of the tin that we mined, that was all right. Deduce the maximum, that was all right. The problem that we've got here is calculating the mass of tin that will be mined in 2023. So this was, people struggled with this, and it's sort of more a numeracy question really. To get the mass in 2023, you've got to work out the mass at the beginning of 2024, because that would be the end of 2023. In the beginning of 2024, you're starting off at 19. You're going to have n equals 5 is the thing to substitute. So that was tricky from a numeracy point of view. You know, we're going to get very good mathematicians making a mess of this. because of that reason. So we needed n equals 5, and doing that substitution, which of course gives us 1200 minus 3 times 5 minus 20 all squared, and then we also had to do n equals 4, in other words finding the end of 2022 and substituting that in. 1200 minus 3 times 4 minus 20 all squared, and then subtract the two away from each other. So there is nothing to revise here or look over other than if you got this question wrong, just take your time over it and just tune into these words here, that it was January and it wasn't the end of the year, it was the beginning of the year. That's why these numbers maybe seem like one more than they were. You know, people were putting n is 4 and n equals 3, but they missed out that the month there was January, and also some people just plugged in a number, n, and they missed out that it was a total mass, and so just for 2023 meant that you had to do some subtracting. So, a difficult question, not because of the maths, but because of the wording, and that will be down to you doing lots of practice at those kind of questions if you want to get good at them. Let's have a look at question 10. We were given the equation of a circle and we needed to write it in centre radius form. So it is, you wouldn't necessarily do this, but what we'll do is if we just gather these terms up and rearrange them a little bit to get the x's and y's together. The idea was to complete the square on these terms. So halve the 4, square it, just do that in your head. X squared minus 4x plus 4, so just subtract the 4 so they're equivalent. Same with the other one, y plus half the 8, 4, square it of course, y squared plus 8y plus 16. It's not quite equivalent yet, just put minus 16 and then just finishing that off. That does give you, of course, x minus 2 squared plus y plus 4 squared is equaling to 28. Gives you a radius of root 28, and obviously the centre is 2 and minus 4. The other bit that we'd got was we've got the equation of the line x equals k, and we're saying that points of intersection, tangents, etc. is a big part of AS. So how do you find points of intersection? You do simultaneous equations. So there's our equation. We just need to put into that x equals k. So that gives us k squared plus y squared minus 4k plus 8y minus 8 equals 0. Is just doing the substitution part of that simultaneous equation. It could be very useful actually just asking yourself, what is this, here's a quadratic, but in terms of what? And it's in terms of y. K is just some number. So we've got y squared, if we write our quadratic in standard form, plus 8y, and then we've got these other bits and pieces, k squared minus 4k minus 8 equals 0. Let's have a little look at what that looks like. It's a good idea to just put brackets around all of this, because this is the C part of it. You know, you've got A, B and C, and I think maybe some of us weren't seeing that C part. As with previous questions, we're making use of the discriminant, b squared minus 4ac, such an important part of our maths, and when we have a tangent, of course, that's going to equal 0. We've just got to make sure that we substitute properly into that. So we've got 8 squared minus 4 times 1 for a times c, which is k squared minus 4k minus 8, of course, is equaling 0, and we continue with that to get our values of k. If you, like in this situation, you now have got to find that k and it's not factorising, you're just going to use the quadratic formula for it. but I'm not going to go through that part of it. That's something you're going to have to sort out yourselves. But please, again, just sort of making the point that the discriminant is important, so try to get to grips with that, please. Okay, I'm not going to say any more about question 10. So, question 11 was a question about the factor theorem, but the big sort of overall concept behind this was, can you solve a cubic? All this work going involved in the ability to solve a cubic, and this is just, I love this, you know, being able to solve this cubic here. This cubic doesn't even factorize properly. You know, it's a nightmare to deal with, and yet we're going to use lots of tools that all come together to be able to solve this cubic. I'm going to give you some advice here, and that is, if you got question 11 wrong, do it again and again, and make sure that you are really, really comfortable with it, please, because it's just got so much stuff going on in it. The first part just said prove that x minus 4 is a factor of f of x. They are helping you here. You know the way to solve a quadratic is to factorize. The way to solve a cubic is to factorize. They're telling you a factor. So even if you can't do this part of it, and you maybe got stuck with that, please use that information to start factorizing. Some of you launched into long division. I've got to say, I was so impressed with your long division of polynomials, absolutely brilliant. But what we want to see here, please, is f of 4 is the substitution. You do the full substitution, please. So put in 4 every time there's an x. And of course, the factor theorem says if that's so, what you will get when you substitute 4 in is 0, which is indeed what you get. You must show that full substitution, right? You've got to actually do that full substitution part. And if f of 4 is equal to 0, it implies that x minus 4 is a factor. Actually, it's an if and only if. It also works the other way, so it's not a bad idea just to put this arrow going that way as well, that if x minus 4 is a factor, then f of 4 is equal to 0. So, yeah, well done to those people who got that bit right. The next part said, hence using algebra, show that the equation f of x equals 0 has only two distinct roots. So in other words, when all of this lot is equal to 0, has these two distinct roots. You can see them there. This one is of course going to be a repeated root. And what you did with that was long division. I'm not going to go over the long division bit of this because most of you got that right, which was absolutely brilliant. All right, well done to see that long division in action. If you can't do long division of polynomial, you're going to have to read up on it, please. It says the next part, C, is worth a quick mention, I think. Deduce giving reasons for your answer the number of real roots to this equation. Now then, this is one of these wordy questions where we're saying, is there an opportunity for a number to be involved here? And the answer to that is yes. Just look at comparing this one. Our function has gone down by 2. Can you see it says 46 and 48? So what we ought to say really is that the left-hand side of this equation represents a translation of f of x by going down by 2 is absolutely fine. So we want to include a number in there. So I'm going to write 2x cubed minus 13x squared plus 8x plus 46 is a translation of f of x. How is it being translated? By, I'll just put 0 minus 2. That means, of course, that from the graph would cut the x-axis at 3 points. So the graph, this graph here, if you like, will cut x-axis at 3 points. All right, so that's enough for that. I think we've done quite well. Another question about translation. A little bit disappointing to see the exam board write this as y equals f of x rather than just f of x. That would have been a lot nicer, and it would have helped us in our notation, which is a little bit frustrating. However, it's not a problem. It was nice to see on some work that people had actually put some numbers in here, that they've got 4 and they've got minus 1.5. And that clearly, if you've got a function, this represents translation just going along, and to do that, of course, if it's going to go through the origin, that would be one way of doing it, going that way. Slightly counterintuitive. I think you're all kind of aware that it's sort of a little bit counterintuitive, these translations in the x, along this way, along the horizontal, is that it sort of is not quite how you'd imagine it, that plus 4 goes that way. So k is equal to 4 would mean the translation goes over there. Take your time over just getting your head around what happens in this direction. That's moving it over this way, and that means that k is equaling a translation of minus 1.5. all right, to move it over in that direction. The reason why is that you want to move the whole graph 1.5 along for that dot to appear there. And when you want graphs to move over in this direction, you have to subtract. All right, so that's where you're getting that minus 1.5 from. That is enough said about question 11. Let's have a look at question 12. Yeah, this is quite interesting. Question 12 was a question about using trig identities to solve equations, and it carried on, it sort of continued the work that you did at GCSE on solving equations. Anyhow, let's have a little look at it. Yeah, you probably recognise this kind of thing, where you get a quadratic on the top and a linear term on the bottom from GCSE, and it said simplify it, and the idea was to factorise and cancel down, and I think some people recognise this. This question was done incredibly well, and it was really good to see that you had to use Pythagoras' theorem. So just this identity, just if you're not sure, of course, cos squared x plus sine squared x is equal to 1. Just that bit of Pythag that we want to be aware of, that if this is a triangle, then sine is opposite over hypotenuse. So if your hypotenuse is 1, opposite over hypotenuse is just going to give you sine, cos, etc. So this sort of picture is fundamental to our trigonometry. You've got to appreciate that. I'll just put a little line in there just saying it's equivalent for all x's. Don't really need to talk about that because it was done really, really well. The other identity that we've got, of course, is that tan x is equal to sine x over cos x. It's a little bit of a shame that some of us missed out on that one here on for that particular one, that identity there. We sort of missed out on, unfortunately. Do we need to talk about it? I think so. I think we probably ought to, really. But anyway, you were thrown a lifeline as well, because you've got to show that question. So that means that you can start to rewrite that equation as 4 minus 5 cos. It says theta there, it doesn't matter. We're going to call it x. And that would be equal to 4 plus 3 sine x. Is what you've got for part B. That does give you, I'm not going to do loads of work on this. You sort of get rid of the 4's, and we divide both sides, of course, by cos x. Gives you minus 5 equals 3 tan x, and it gives you, of course, that tan x is equal to minus 5 over 3. Gosh, I'm being a bit tedious, sorry. And that x is equal to the just inverse of tan of minus 5 over 3. When you do that in your calculator, Your calculator gives values sort of between plus and minus 180 when you inverse trig functions with them, and here it gives you minus 59.0. What I would do whenever you get a negative, because we don't want negative answers here because it was between 0 and 360, is just add 360 to it. You know, you can always add 360 to anything that you're doing trig-wise because they're obviously starting to repeat. So another value of x that you've got straight away is 301 degrees. All right, you have got to find the other one. Some people drew the trig graph, and I think that's okay in year 12. As we're carrying on, I don't think it's such a good idea. Let's just have a look at that. This is, you know, these kind of diagrams I think are better. That's just my view. Minus 59 would go down like that, or 301, which comes right round like that, so it's the same thing. The tan is the gradient. Is there another point? Let's just put, I'm just going to put in that, you know, 301. Is there another line that also has the same gradient? Just carry the line on. Right, it's that line there. And then I'm not going to say anything other than that. Then look, it's just, you know, angles on a line add up to 180, etc. So it's not too difficult for you to work out 121. What I will ask you to do, please, is when you're, you know, if you need to do a bit of extra work over the summer, make sure you're okay with working out all the values of your trig, because trig is something that we build on, and it is essential that you get really comfortable with it. So look at how do you take what we call a principal value and then work out other values from it. Right, so make sure you can work out all the other values that give us what we want with trig questions, please. That's really important that you go over that again. You know, some things in maths we sort of leave alone. It's a bit like GCSE, we do circle theorems and don't really see an awful lot of it, and then other things we need to sort of be aware that we'll have to go through them again and develop them. Question 13 is your question about area under graph. So there was it's an integration question. I think most of us were sort of okay with it. It says we've got a turning point there, so we needed to differentiate this thing. I think you could differentiate that okay, and I think you're also able to set it equal to 0, and you should have had that we've got a turning point here at x is equal to, I think it was 5/3 if my memory serves me correct, and this one was 4. So that bit was done pretty well. If you can't do that stuff, make sure please that you can differentiate and then use the gradient function to work out points when the gradient is equal to 0, in other words turning points. Okay, then what did you have to do? You had to do some integration. I think this was fine really. The only thing I would pick up on is just make sure that your notation is okay. So we wanted to see some working that looks something like this. You're integrating between these two limits, 4 and 0. Open up your bracket please to put in the thing that you've got. You've got the function there, 2x cubed minus 17x squared plus 40x dx. So it was really just a question of please be a bit tidier with your notation. There is nothing admirable at all about showing how quick you are with your working and that you can quickly do it on the back of an envelope. That's great just to hack something out like that. That's brilliant as and when needed. However, when it comes to the exam, a big part of what you're doing is communicating. So we're very, very fussy about that. Don't use the elongated S at this point. Use the square brackets and actually do the integration part of it. A very straightforward integration to do for this question. You should have something like that with those limits in. So that's what you're working out each time. You can put an equal sign if you want to. It's not the end of the world if you don't. You've got to do the full substitution. I say the full substitution. I don't want to contradict myself, but you know, when you put in all this stuff, just I'm sorry if this is wrong. I'm trying to do this quickly, but I don't think actually I'm going to put 0 in there. That would be, let's draw a limit. Let's draw the line somewhere. I think that's going to be absolutely fine if we do that. Anyway, we should get 256 over 3 as our final answer. So a fairly straightforward standard question. Please make sure you're okay with the standard questions. You don't want to make a mess of them. There's very little problem solving involved in that, so get that sorted. Okay, question 14. Question 14 is the exponential model. So modelling, are we getting this, graphs, line graphs, whether it's straight lines, a linear model, quadratic models, and then now an exponential model. So the third modelling question. You can see just how important this is. This was okay, except that you haven't spent much time on being able to differentiate something like this. Let's just pick up something here. It says, given the model predicts that the value of the car is decreasing at a rate of 500. We could have said it's increasing at a rate of minus 500, but we're saying decreasing. Now, when you see this word rate, it means 500 per year. That means the change in value with respect to time. So when you see the word rate, think dt, something dt, whatever it might be. And here it's dv by dt. All right, just in the same way that we'd say what would be, something is changing its position, at so many meters every second, at a rate of, or per second, we would think dv by dt, so ds by dt, or whatever. So anyway, enough of that. Sorry, I'm going on a bit. We're told it's decreasing, minus 500. So that's what you have got. That was the tricky part of this. And as soon as you've got that bit, then you're into some differentiation. We've not practiced much of this differentiation of e to the power something. So it's actually incredibly easy. When you come to do it, it was minus 0.25 times 15700 e to the minus 0.25t. It's incredibly easy to do, is equal to minus 500. All right, and you carry on from there. So differentiating e to the x or e to the t or whatever is very straightforward. If y equals e to the kt, then dy by dt, I should have put x there, it doesn't matter, whatever, sorry, is equal to k e to the kt. So it's just something that we learn, all right? And you can come back to this later about why that is true. Maybe what's more important, actually, is this last bit that says state a limitation of this model. And here, it's not that the model is invalid, it's just, it's maybe more simple than the other ones, just for a quick 1 mark. And if you get something like this with exponential models, it's a good idea to think about what's happening over a long period of time. And over a long period of time, in this case, what could happen to the value of the car? It might be if the car is still in good condition, that it would increase its value because of its rarity, and that's it. Not going to say any more about question 14. Question 15 was done very, very well indeed. Well done to those people that did the proof question. If you didn't do this, there's not much proof in AS. There is proof by contradiction, and there's also proof by exhaustion. Another term for proof by exhaustion is proof by cases, which is really useful, actually, more than exhaustion. So people that tried to do it by exhaustion, in the sense that they tried to put every single value in and showed, they can't do every single value, so they did like half a dozen values. It's just not enough, I'm afraid. So proof by cases is a good way to think of proof by exhaustion. And here we'd say, what about when n is equal to odd, for instance, and do it like that. If you're unsure how to tackle this, if you've got an odd number, if n is odd, then there must exist some n, which is also an integer, such that n is equal to 2m plus 1. That's what n could be written as. All right, so there must exist some m such that n could be written like that. And instead of saying n, what does that say? N cubed. Instead of saying n cubed plus 2, just say that cubed plus 2. And you could actually expand the whole thing and show very clearly, in actual fact, that what you get is also odd. In this particular case, if n is odd, n cubed is also odd. If n cubed is odd, it also means that n cubed plus 2 is odd. And you can't have an odd number which is an integer of 8. So can't be a multiple, of 8. Not possible. The other case, I'm flagging, sorry, just bear with me, sorry if I've made a few mistakes, is there must exist some m so that n could be written as 2m. And again, you could write that as n cubed plus 2 and just see what happens, what you get in this case, which of course is that. This is a slightly different argument here. You're just saying 8m cubed is a multiple of 8, and therefore 8m cubed plus 2 cannot be a multiple of 8. So that's how we were expected to do it. You can't just do a few values of n and say, oh, it seems to be right. You have to show it for all cases. Question 16, but I tell you what, done incredibly well actually, very impressive. Question 16 was, the first part was difficult. Well done if you got this first bit right. And it says two non-zero vectors A and B are such that those lengths are equal to each other. It's worth just noting that there's lots of different applications for vectors, and the only application in fact that you use at A level is for journeys, as it were, is geometry. That's the only application you use at A level. It's the only application in further maths as well, or any of the A level courses. So actually vectors are really just restricted to geometry at A level, which is a useful thing. And the way that we use vectors to describe journeys is to define the addition of vectors as being those journeys putting end to end. A starts there and finishes there, so A plus B looks like that. Alright, so that's the definition. There's no maths there. We are defining a journey to we're defining A plus B to be like this, and we will use what we know about vectors to work with geometry. So actually at A level we just refer to these as vectors anyway, so it's not an issue. Right, stop waffling on, do the question. These lines of course mean just the length of it. We're told that the length of A plus B is the same as A plus B. You can't just say that. You can't just say the length of A plus B is the same as the length of A plus the length of B. If that is true, you must get this situation, in fact, where A would have to be like this and B must be like that. They are suggesting something incredibly nice here, actually, in terms of your mathematics, and some of you will carry on with your maths. Your maths journey won't end at A level. You'll continue with it, and there is a concept in mathematics, in vectors, which is very important actually, and it's this this concept here. It's called the triangle inequality, and it's such a simple idea but is really useful. So that's what they're getting at, that if that's equal to that, these lines have got to be in the same direction, parallel in the same direction, etc. Let's see if we can make some sense of part 2, because it was actually a slightly contrived question in terms of vectors, but I understand that because it's AS level. Let's just do it. Two different vectors, m and n, are such that the size of m is 3 and the size of m minus n is 6. It's going to be very good for you to understand what m minus n looks like, and I'm just going to draw it for you. So I'm just trying to think of the best way of doing this. I want to make sure I don't make a mess of it. I think what I'm going to do is I'm going to say m is going to go like in that direction, but I'm going to do an n coming off it like that. So just as we've got an application of adding vectors in terms of journeys, we can do something similar for taking away. Now then, we've got m take away n, but I'm going to think of m take away n as being minus n plus m. Right, they're the same thing. And if we're doing minus n, it means we've got to start our journey here, go minus n and plus m. So you would end up there. In other words, you can get the direction of your arrow. So this picture is a very important picture actually, and something that has been overlooked, that I've overlooked, I'm afraid, as in delivering this stuff. Hey ho, but that's the picture that we want to see, that m minus n is minus n plus m. It gets you from there to there. Try to, get your head around that and make sure you're okay with it. Then what you can do actually is just reduce it to a GCSE question. So it says the size of m is 3, the size of m minus n is 6, the angle between m and n is 30. So that's the picture that we would have, sorry, you can't see this. That's the picture we would have ended up with. Use the sine rule. Now then, just as a point, sometimes the simplest things can throw us. You think, right, the sine rule, I get that. That was, if I've got sine 30 over 6 would be equal to something over 3. Oh, which angle? That angle. Oh, hang on a minute. I'm asked to work out the angle between m minus m. I'm asked to work out that angle. Oh no, I can't do it. Yes, you can. So just work out that angle. Work out y. All right, so sine y. And don't worry that it's not the angle that you want, because you can always use the cunning fact that the angles in the triangle add up to 180. All right, so just don't be put off by those things. I feel your pain if you got confused there. Sometimes it just happens. You can just kind of think, oh, of course, I don't need to worry about it. Anyway, that's enough said. You should have got that x was equal to 135.5 degrees. Where people went wrong with this was this picture here, getting that picture. And I understand that because we've not done much of that at all. Okay, so anyway, well done.